Okay, consider this system now. From a square-shaped plate, 1/4 has been removed. Okay, the remaining system is shown to you. The side of the square is A, that is also indicated in the diagram. Center of the square is at the origin. Center of the original square, okay, is at the origin. Assume the mass is uniformly distributed. Derive the position of center of mass of this system. Try this, both of you. Any answer, anyone? Okay, Aishwarya, how are you trying to solve this? No response. Rishi?
Sir, if the fourth part would be there, it'd be a square, but I'm not sure as to how to do it with only three of them. As to if I should take like each square as different, or
See, if that is one of the ideas which can be used to derive position of center of mass, use it. If you can treat it as a collection of, see, it's one of the ideas we had discussed, right? A system can be treated as a collection of smaller systems. So if you think you can do it that way, proceed that way.
Sir,
Yes, Aishwarya.
sir, I got the answer as A by 6, but I'm not sure with it.
You have to tell both coordinates, x and y. Anyway, what is your idea?
Sir, at first I considered it as a square.
Full square.
Yes, sir.
Okay, and then?
And then I tried finding the center of mass of the full square.
Where is the center of mass of the full square? Had it been complete?
A by 2, comma A by 2.
Center is the geometrical center. No, geometrical center is the origin. Like x-axis, y-axis are already given to you. You can't change it. I mean, your answer would be correct. Had this been the y-axis and had this been the x-axis, then the full square center would have been a by 2, a by 2. Okay, anyway. And then after that, what will you do?
Sir, and then I found the center of mass of the the square that's missing.
Okay. So you tried to use the negative mass idea.
Yes, sir.
Okay, fine. That's one way to solve. Vanilla, how did you derive the position of center of mass? Okay, listen, all of you. Vanilla, you unmuted, but I'm not able to hear anything from your side. Let it be. Listen, all of you, there are two ways to solve this problem. Okay. Like when I gave the question or gave the problem, I expected you will treat it as a collection of systems. Because we know where the center of mass of a square lies, at its geometrical center. So what you can do is you can treat this system as a collection of three squares. First square has its center here. What are the coordinates? If the total side is A, then this will be A by 2 and half of it will be minus A by 4. X coordinate is minus A by 4. Y coordinate is plus A by 4. Those are the coordinates of center of mass of the first square part. Then the second square part, its center of mass lies here. Its coordinates, its x coordinate is minus A by 4. Y coordinate is also minus A by 4. It's in the third quadrant. Both coordinates will be negative. And the third square its center of mass is at a by 4 comma minus a by 4. So now you treat it as a collection of systems. Each square is a system now. And what do you do when you have to find out the position of center of mass of a combination of systems? Each system will be treated as a single particle placed at its center of mass. So we are going to treat these plates as particles now. Okay. And how do you find out the position of center of mass of a 3-particle system? RCM is equal to M1R1 plus M2R2 plus M3R3 divided by total mass. M1 plus M2 plus M3. Now we know R1, R2 and R3. We know their positions. What we need is their masses now. And we had discussed this point before also. In fact, we used it in many problems. To find the position of center of mass of a system of particles, you don't need to know their exact masses. You only need the ratio of masses. Now I told you this system is uniform mass distribution. Therefore, each of these squares will have the same mass m. Okay, so all masses are equal. Therefore, if you want the x coordinate of center of mass, you do m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. That becomes 3m, and m gets cancelled because it's common in the numerator and denominator. That's why I said it's only the ratio of masses that matters. Actual mass doesn't matter. That's all. A by 4 cancel. Minus a by 4 divided by 3 is minus a by 12. That's the x coordinate of center of mass of this system. Okay, and finding the y coordinate is not very difficult. This system actually, if you observe, it has a line of symmetry. This is the line of symmetry passing through the origin. Okay, and you know that if a system has a line of symmetry, center of mass should lie on that line. Now this line, as you know, is y is equal to x. Both x coordinate and y coordinate will be the same for that line. So if x coordinate of center of mass is minus a by 12, then the y coordinate of center of mass, you can calculate if you want, but I can directly tell it will be minus a by 12 itself. Okay, therefore the position of center of mass of this system is minus a by 12 comma minus a by 12. Some of you gave answers as a by 6. Maybe you took the positions wrong. You took it as a by 2 or something, or you changed the origin to some other position. Could have happened, but for the given origin, this is the answer. Is this method clear to all of you? Rishi, did you understand?
Yes, sir.
Okay, I got one doubt as how is it 3m in the denominator? See, denominator is the sum of all masses of the system. Okay, each square has a mass m, then the total mass is 3m. Okay. Now, I'll tell you another way to solve this, the way Aishwarya tried to solve. For a full square, okay, for a full uniform square, we know where the center of mass lies. Okay, we could have made use of that also. Let me erase all these. Okay, follow this approach carefully. This is important. We are going to be using it in the derivations that we do next. Imagine the given, I mean, it's not a full square actually. You're not given a full square, but assume a complete square was given to you. Rishi, tell me, where would the center of mass of this complete square have been?
Geometrical center, sir.
Geometrical center, that is the origin, right? Okay. You can treat this as a collection of just a moment, just this one time for visualization, we'll have to do all this. 1 second. Okay. The given system can be imagined like this. Okay, sorry, not the given system. The full square can be imagined like this. The full square is the combination of this L-shaped part plus the remaining square bit. Therefore, the L-shaped part can be considered as full square minus the square bit. That also can be done. We just need to rearrange this. Did you all understand what I said? The L-shaped part is the full square minus the small square. Yusuf, is this point clear or not?
Yes, sir, clear, sir.
Okay. Let me write it that way. You'll understand why we take it like this, or how it is useful if you take it like this. The L-shaped object is the combination of a full square minus this small square part. Okay. You are asked to find out the position of center of mass of the L-shaped object. Fine. The idea here is to treat the given system. Okay, see, this is the given system. The given system seems to be a symmetrical system from which some part has been removed. This is the removed part. Okay, such situations are quite common. From a regularly shaped system, from a symmetrically shaped system, some part will be removed. In such cases, what you can do is treat it as a full system of positive mass. Now from that, you have to subtract that mass, that square bit. Instead of subtracting, what you can do is you can add something called a negative mass. Imagine this mass to be negative. See, in reality, there is nothing called negative mass. Okay, but you can imagine something like this, that just for the purpose of solving problems. So full square positive mass plus small square negative mass gives you this. It's like writing 3x is equal to 4x plus negative of x. That's all, where x represents each part of the square, each quarter of the square. Now, what is the advantage of taking it like this, or what is the use of taking it like this? The given system, this L-shaped object, is now being treated as a combination of two systems. This is one system for us, and this is another system for us. Now, some of you may say, sir, we already treated it as a collection of systems like this, and we easily got the answer. Why all this headache? Okay, you are learning a new way to solve problems, which will be useful in some cases. The given L-shaped part was a proper collection of three squares, so doing it that way was easy. Treating it as a collection of three squares and solving it was easy, but just learn this new method also. So we are treating it as a combination of systems now. One system has positive mass, another system has negative mass. Let it be. Now, when you treat a given system as a collection of systems, what do? You replace those systems with single particles placed at their center. Rishi, tell me, where is the center of mass of the full square?
Origin, sir.
At the origin, correct. So we'll assume there is one mass present here. We'll call it M1. Okay. Yusuf, tell me, where exactly is the center of mass of the small square? The removed part.
So in this geometric center.
Okay. Can you tell its coordinates? Like,
So A
the,
comma. So if you use A.
wait. The full square side is A. So part, like 1/4 side is A by 2. Based on that. Like this side is A by 2.
So then. Right. So A by 4 comma A by 4.
Correct. A by 4 comma A by 4. Fine. Let's call that mass as M2 and its coordinates are A by 4, A by 4. But M2 is a negative mass. Fine. What we need is the position of center of mass of the combination of these two systems. Okay. We found out where their individual centers are. One is at 0, 0. One part's or one system's center of mass is at 0, 0. The other system center of mass is at A by 4, A by 4. What else do we need to derive position of center of mass? We need the ratio of their masses. Okay. Pawan, tell me, what is the ratio of masses of the full square and the small part?
M1:M2.
Array. How much is that ratio I'm asking? You can look at their sizes and tell, no?
Sir, 4:1.
Correct. 4:1. What kind of a mass distribution is this? Listen to this, all of you. Some of you may have easily found that it is 4:1, but there is an explanation also for it. Pawan, what kind of mass distribution is this? Linear, aerial, or volumetric?
Sir, aerial.
Aerial. It's a square sheet, okay? It's an aerial mass distribution. For aerial mass distribution, mass ratio will be equal to area ratio. And the big square and the small square, their area ratio is 4:1. Okay, so mass ratio will also be 4:1. So there is a mass of 4m here, and the m2 is just m, and we are treating it as a negative mass. So you have to take it as minus m. Fine. Only if you treat it as negative mass, the collection of these two becomes the original system on the left. Okay, so one mass is 4m, the other mass is minus m. As it is, we'll substitute in the formula for center of mass. So 4m is at 0, 0. Minus m is at A by 4 comma A by 4. Therefore, if you want x coordinate of center of mass, it will be m1 x1 plus m2 x2 divided by m1 plus m2. m2 is negative, you have to substitute negative. Now how much does this become? First term is 0 anyway. Minus m into A by 4 is minus m A by 4 divided by denominator 4m minus m is 3m. M gets cancelled. You will still get minus A by 12 as expected. Okay. When we treated the full square as a combination of three small squares and solved it easily, we got x coordinate as minus A by 12, center of mass x coordinate. Even if you treat it this way, you will get the same. Okay. So basically the idea is that from a symmetrical mass distribution, if some part is missing, you can treat such systems like this. You can treat it as the full system, you can treat it as a combination of full symmetrical system and the missing negative mass, and the missing part has the negative mass. But you should be cautious. You have to take the mass ratio proportional to the length or area or volume, depending on the kind of mass distribution that is given to you. Is the idea clear to all of you? Did you understand this method? Rishi, did you understand what we did?
Yes, sir.
Okay, let's see if you all can apply this. Consider a system like this. The actual mass need not be given to you. It's just based on mass ratio that you find out the position of center of mass. Again, assume the side is A itself, full side is A. It's a square plate. From this square plate, what we are going to do is we are going to remove some mass. Let's say the removed mass is like this. Assume what is removed is also a square itself. Okay, like here it shows rounded edges, but you assume square edges. I mean sharp edges. You have to find out the position of center of mass of the remaining system. Now, what is the side of the square that has been removed? Now, total side is A, so half of it is A by 2. This side is A by 4. Okay. Derive the position of center of mass of the remaining mass. Try. Okay, I got one answer as minus A by 120 minus A by 120. Okay. Let's see. See, this system has a line of symmetry. And the line of symmetry is again the line y is equal to x. So if you find out the x coordinate of center of mass, that is enough. Y coordinate also will be the same. Okay. If you want to treat this as a combination of systems, like combination of positive masses, then it will become complicated actually. You will have to treat it as a combination of many small bits like this. One here, one here, one here, 3 in this and 4 in each of the other parts, other quarters. Okay, so many objects and their centers of mass will have to be considered if you want to treat it as a collection of objects. Another way to solve it is treat this as 1, treat this as 1, this as 1, and this as 1. But you will first have to find out where the center of mass of this part lies, how much mass it has, and then treat it as a collection of these 4 systems. That is also quite complicated. Okay, the easier way to solve would be by using the idea of negative mass. Okay, I repeat again, negative mass doesn't exist in real life, but it's a technique which will help us solve problems like this. Okay, this is clearly a case of a symmetric mass distribution missing some part. Okay, so we can make use of negative mass to solve such problems. So you can treat the given system. You have to imagine all this. They won't give you all this in the question. No? You can treat the given system as a collection of masses like this. First, the original system is equal to the full system plus the removed mass will be treated as negative mass. So just a moment, let me adjust all this. What was removed is a small square bit from here, like this. Okay. So the given system is equal to this much positive mass. Okay, the full plate will be taken as positive plus a small negative mass. Okay, the missing part will be treated negative mass. Now it's simple. There are only 2 objects whose combination gives you the original system. Now, again, same combination of systems idea. When you have to find out the position of center of mass of a combination of systems, each system will be replaced by a single particle placed at its own center. Okay. Now the original square, its center is the geometrical center. We know that. Let me mark that point. This one. The original squares, the entire mass of the original square can be assumed to be present at this point, which is the origin. So 0, 0. How much mass to place there, we'll discuss. For the removed part, the center of mass is here. If its side is a by 4, then the coordinates of that point will be a by 8, a by 8. Okay. Yusuf, can you tell me the ratio of masses of the full square and that small bit? Ratio of masses of the full square and that small square. See, it depends on how the mass is distributed. Now, this is a square plate from which some part has been removed. Square plate is an areal mass distribution. Mass is spread over an area. Then the ratio of masses of two such systems will be the ratio of their areas. Okay. Full square side is A. So full square area is A square. Removed part side is A by 4. Its area is A square by 16. So the ratio is 1 is to 1 by 16, or you can say 16 is to 1. Therefore, you can assume a mass 16 m to be present here and a mass minus m to be present here. Okay, from that 16 m, if you remove the m, okay, you get this remaining mass. That is the original system that is given to you. Yusuf, did you understand? So 16 m is at 0, 0, minus m is at a by 8, a by 8. That's all. After that, you just have to apply the formula for position of center of mass and solve m1 x1 plus m2 x2 by m1 plus m2. Okay, I'll leave the remaining part. You can solve it on your own. Next, one last question of this kind. After that, we will move to moment of inertia. This question is quite common actually in any material you will find. From a circular disk, okay, let's say some part is removed. The removed part is also in the form of a circle itself. Okay, assume the situation is like this. So full circle radius is r. The removed part, you can see like from here to here, if it is r, from here to here would be r by 2. Then the removed part's radius is r by 4. Okay, you can see where the origin is. You write the coordinates carefully. Removed part radius r by 4. It's a circular plate from which some part has been cut out. The part that is cut out is also in the shape of a circle itself. So it's an areal mass distribution. Treat it as a combination of masses, full positive mass and small negative mass. Distribute the masses proportionately. Derive the position of center of mass. Solve carefully, all of you. I'll give you 3 minutes. I got only one answer as minus r by 20. Okay, we'll see. Aishwarya, any answer?
Sir, I got minus R by 20, sir.
Fine. Pawan?
Sir, almost ending now.
Okay. Yusuf, any answer? See, this is clearly a case of a system, of a symmetrical system from which some mass has been removed. Now, this problem has to be solved by using the idea of negative mass. You can't treat it as a collection of small parts because you can't even tell where is the center of mass of this part. Okay, for the others also it's quite difficult actually. We don't know where is the center of mass of a quarter circle. Fine. So we'll treat it as a full circle of positive mass and a small circle of a proportionate amount of negative mass. Okay, so I'll mark the full circle in green. So we'll have to assume there is this much positive mass present. Can one of you quickly tell me where is the center of mass of this positive mass? Okay, it's a symmetric
Sir,
mass
if
distribution. Yeah,
if
tell
the
me.
whole mass was that there was no missing part, it'd be the center, but like now it'll be towards the left of it.
It'll be shifted to the left. Okay, good. So the positive mass, its center of mass is 0, 0. Okay. And this system has some negative mass also. Let me highlight the negative mass. Negative mass is this much. Okay. From the full system, if this negative mass is system, if this negative mass is removed, you'll get that cavity there. Okay. Cavity is nothing but empty space. And that removed mass, its center of mass is here. What are its coordinates? 0, no, not 0. X coordinate will be, total is r, that side is r by 4. So this side will be 3r by 4, 0. These are the coordinates of center of mass of the removed mass. Okay. The green mass has to be taken positive. The red mass has to be taken negative. Fine. Clearly the green one is more than the red one. So we need to find out the ratio of positive mass to negative mass. Now this is a circular plate or a circular disc from which some mass has been removed. A circular disc is an areal mass distribution. Positive mass area, since its radius is r, the area is pi r square. And negative mass area, negative mass also is in the shape of a circle only. Its radius is r by 4. So the negative mass area is pi into r by 4 squared. It becomes pi r square by 16. So area ratio is 1 is to 1 by 16. That's like 16 is to 1. So the mass ratio will also be 16 is to 1. So you can treat positive mass as 16m, negative mass as minus m. These are what we are going to use. So 16m is at 0, 0 and minus m is at 3r by 4, 0. That's all. Therefore, the x coordinate of center of mass of this combination will be m1 x1 plus m2 x2 divided by m1 plus m2. 16m minus m is 15m. M gets cancelled. 4, okay, 3 5s is 15. 5 into 4, the answer is minus r by 20. The x coordinate of center of mass of this whole system is minus r by 20. And yeah, Rishi, as you said, the full system center had been at the, would have been at the origin. Since we removed some mass from the right side, center of mass shifts to the left side. And that's the answer that we got. Minus r by 20, 0. We didn't even bother to derive the y coordinate of center of mass because the systems that we took, the full circle and the small circle, their centers lie on the x-axis. So the combined system center of mass will also lie on the x-axis itself. So no point deriving the y coordinate, it will be 0. Okay. So remember the idea from a regularly shaped system, if some mass is missing, this is how you approach. How much is the full mass? How much is the missing mass? Like you just need to know the ratio. Okay. Next worksheet, you'll have more some more problems like this. And last worksheet, nobody submitted. Okay, anyway, you may be busy with school exams and all. That's fine, but you ensure you are thorough in the subject, whether you are learning it from school or from me or from some other source. There's this chapter system of particles going on. Okay. Suppose you learned it thoroughly in school, then no problem. You don't have to solve the worksheets that I'm sending. Suppose you are relying on these classes only to learn, then you have to solve worksheets. Otherwise, I mean, the learning will not be complete. Even if you are studying from school, no, just listening classes is never enough. You have to apply what you learned. You have to apply what you learned in new situations also. Okay, some extra thing. You have to extend your applications and thinking. All that is there in the worksheet. Such questions are there in the worksheet. Okay, so take time and solve those questions. Fine. Let's continue the chapter. See, what is the topic that we are discussing? System of particles and rotational motion. Okay, now where did we come across this thing called center of mass? Basically, in systems which rotate, different particles move with different velocities and different accelerations. Okay, they'll not all move in the same manner. To describe the motion of such systems, there is this magical point called center of mass which helps us. How it helps, we still haven't gotten into the details. For now, we only identified where that center of mass is. Okay, we discussed some cases or some situations where center of mass helps us. Fine, where like velocity of center of mass. Okay, as you see, the formula is m1 v1 plus m2 v2 so on divided by total mass. Basically, velocity of center of mass is the net momentum of the system divided by total mass. So if you want net momentum of a system which undergoes complicated motion, then you can write it as total mass of the system and multiply it with velocity of this one point called center of mass. Infinite different particles of the system will be having infinite different velocities. But if you know velocity of center of mass, you can tell the momentum of that entire system. That is one way in which center of mass can help us. Next, application of Newton's second law, F net equal to ma. Now, if different particles of the system accelerate in different ways, which particle's acceleration should be considered to apply Newton's second law? It is the center of mass's acceleration. That comes from the definition of center of mass. Okay, so if you want to apply Newton's second law to a rotating system or a system which undergoes complicated motion, you will have to look for the center of mass. Okay, fine. These are two obvious applications of position of center of mass. Let's discuss one more idea now. Can any of you tell me the formula we used for gravitational potential energy? Last chapter we discussed conservative, non-conservative forces. We discussed potential energy. We derived a formula for gravitational potential energy.
MGH.
MGH. M is the mass of the object whose potential energy you want to calculate. G is acceleration due to gravity. What is H? In the formula for gravitational potential energy, what is H? We used it many times in mechanical energy conservation and all. H is the height of the mass M above the reference level. You first need to choose a reference level, a certain horizontal level where you are going to take the potential energy as 0. Then at a height h above that level, the potential energy will be mgh. Okay, we applied it to blocks, balls, particles, whatnot. But what if you are given a system whose dimensions are significant? Suppose there is a person standing on the ground, okay, and you want to express the potential energy of the person, gravitational potential energy of the person. How can you do that? Okay, let me give you an example. Just a moment. Suppose this person's mass is some 80 kg. And let's say the person's height is approximately 2 meters. Okay. Pawan, what do you say? How can we express this person's gravitational potential energy?
అంటే ఫార్ములా సబ్స్టిట్యూట్ చేయమని చెప్తున్నారు లేకపోతే
అంటే ఫార్ములాలో సబ్స్టిట్యూట్ చేయడం వ్యాలిడేనా లేదంటే ఎట్లా చేయాలి? దట్ ఈస్ వాట్ ఐ వాంట్ యూ టు థింక్.
వ్యాలిడే సార్.
Okay, so you are saying we can use mgh here. Then in that case, your answer for potential energy of this person will be 80 into 10 into 2, 1600 joules.
సార్ ఒక డౌట్
Yeah, tell me.
సార్, అంటే మాస్ మనం గ్రౌండ్ రిఫరెన్స్ లెవెల్స్ తీసుకోవాలి కానీ 80 కేజీస్ అని మాస్ మొత్తం డిస్ట్రిబ్యూట్ అవుతుంది కాబట్టి రిఫరెన్స్ లెవెల్ ఎక్కడి నుంచి తీసుకోగలుగుతాం?
See, reference you can fix anywhere. Reference you can fix anywhere, but the 80 kg, as you said, is distributed. So,
Yes, sir.
is this correct?
No, sir.
No. Why is this not correct? Because all the 80 kg is not at a height of 2 meters. All the mass 80 is not at height of 2. Therefore, we can't simply use mgh and find out the potential energy of extended objects, because different particles of an extended object will be at different levels above the ground. Okay, so another thing we are learning another thing we learn in this chapter is how to deal with objects whose dimensions are significant. Till the last chapter, okay, all the way from kinematics to work energy power, we never considered height of the block or radius of the ball and such dimensions. Block is on the floor, it's on the floor. Block is at a height 2 meters, the entire mass is at a height 2 meters is how we used to take it. Okay, but now in this chapter there's another thing we learn, how to include or how to account for dimensions of the objects. So yeah, as Pawan correctly pointed out, all the mass is not at the same height. So for different masses of the system, we'll have to assign different heights and find out their potential energies individually. Okay, so let's say this is the reference level. Assume there is a system of particles. It could be a continuous mass distribution. It could be a distribution of discrete particles also. Discrete means separate. Okay, so you can treat it as a collection of particles. That's why the name of the chapter, system of particles. Extended objects should be treated as system of infinite particles. Okay, so suppose there is a system like this. You can see that all mass of the system, all particles of the system are not at the same height from the ground. Okay, so in such cases, if you want to find out potential energy, you will have to write potential energy of the first particle plus potential energy of the second particle, so on up to potential energy of the nth particle. That is how you are supposed to do it. But do you think it will be practical to do it like this? Clearly not, because there will be infinite number of particles. Okay, so let's see what can be done. Consider one of these particles. Let's say this one. Assume its mass is m1 and its height from the ground is h1. Consider another particle, maybe this one. Assume its mass is m2 and its height above the reference level, okay, I should not say ground, I should say reference level, is h2. Okay, another mass m3 at height h3 and so on. Infinite particles could be at infinite different heights. Therefore, the total potential energy of this system becomes m1gh1 plus m2gh2 so on up to mngHn, height of the nth particle. Is this step clear to all of you? Aishwarya, did you understand?
Yes, sir.
And did you understand why the answer is not 0 for the person standing on the ground?
Yes, sir.
All the mass is not at 0 height. Okay, fine. Now, H1, H2 are the heights of the particles above the reference level. You can call them as y1, y2 and so on if you want. Nothing wrong in that. You can treat it as their y coordinate. Okay, so this potential energy can also be written as, take G common, you will be left with m1 y1 plus m2 y2 so on mn yn. Okay, now this is where you should get the hint. Do any of you remember seeing any term of this kind before in any formula?
Y coordinate of center of mass.
Very good. Y coordinate of center of mass. Rishi, can you tell me the formula for y coordinate of center of mass? Of separate particles. No, yeah. The integral formula is correct only, but that's for continuous mass distributions. If particles are separate. Pawan, can you tell the formula for y coordinate of center of mass?
Summation of m y1 by
Summation of
m.
mi yi, where I varies from 1 to n. You have to include all particles, divided by summation of mi. Correct. Basically, this is nothing but m1 y1 plus m2 y2 so on up to mn yn divided by the total mass of the system. Fine. Now in the formula for potential energy, or when we tried to express the potential energy of this system, we got a term like this. And we see the same term here. Cross multiply m to the other side. You can say that m1 y1 plus m2 y2 so on up to mn yn is nothing but total mass of the system multiplied with the y coordinate of its center of mass. This makes our job very easy. Here, there are infinite number of terms. This is just one term. Okay, so it's like center of mass represents all the particles now for potential energy calculations. So this entire bracket can be replaced by m into ycm. Therefore, the potential energy of this extended system or extended object, I'll call it, is equal to m. Okay, I should write capital M, total mass of the extended system. G, y coordinate of center of mass, or you can also treat it as height of center of mass. This is another very useful application of center of mass. If you know where the center of mass of a system lies, you can easily tell its potential energy. Just take the height of center of mass, and this is the mathematical proof for it. Okay, if different particles are at different heights, you have to add the potential energies of individual particles. But in that formula, you end up getting this term m1 y1 plus m2 y2, which we have seen in the y coordinate of center of mass. So m1 y1 plus m2 y2 so on can be replaced with total mass of the system into y coordinate of its center of mass. And y coordinate of center of mass, I wrote it as height of center of mass. Is this clear to all of you? Okay. Let's try some problems based on this. One very simple question. Okay, one of you tell me from what we discussed before, what is work? Mechanical work. What is the meaning of mechanical work? What is the meaning of mechanical work?
Cos theta.
That is the formula. I asked the meaning. And Fs cos theta is only for constant force. For variable force, it is integral f ds cos theta. Okay, but what is the meaning of work? The first question I asked you when we started the chapter work energy power is how you feel when you do a lot of work. Tired means you feel less energetic. So if you do work, if you do mechanical work, you are transferring energy. Work is transfer of energy. Remember that. Okay. Formula is Fs cos theta, but you should know the meaning of the quantity, no? Mechanical work is transfer of energy through forces. Okay. Then when you make it mathematical, it becomes F dot S or integral F dot ds. Fine. So just a moment. Let me take one diagram from the previous class. Suppose there is a solid hemisphere like this. Okay. Initially, it is placed this way. Assume its mass is 2 kg and its radius is some 0.4 meters. Okay. Can one of you quickly tell me where is the center of mass of a solid hemisphere?
3R by 8.
3r by 8 from the base. Correct. That is what we derived in the last class. So suppose there is a solid hemisphere like this lying on a table. It's lying with its circular base facing downwards. You have to invert it. That's all. Okay. Calculate the work required to place the hemisphere on its curved surface. Simple question. Okay. The solid hemisphere is lying with its face down. You have to invert it and make it face up. How much work do you need to do for that? Think carefully and answer. Just a moment. I'll show you one more. Just to help you with the visualization, I'll show you one more diagram. Those of you who understood the question, you can proceed and solve. So when you look from the side, the solid hemisphere looks like this. This has to be changed to this. That's all. In this process, how much work is to be done? Think carefully and solve. I gave you the hint also. Work is transfer of energy. Okay, keep that in mind and solve. Okay, I got one answer as 2 joules. We'll see. Pawan, how are you trying to solve this? Did you get any idea?
No, sir.
Okay. Aishwarya, what about you?
Sir, I wrote change in potential energy is negative of work done.
Okay, that is a good idea, but fine. There's a problem with the implementation. We'll come to that. Rishi, any idea?
I'm not sure.
Yusuf, if you can unmute.
No, sir. No clue.
Okay. See, Usually work is calculated in terms of force and displacement. Here we don't know the force and displacement, like we don't know what exactly has happened here with this object. Like while inverting it from position A to position B, we don't know where all it has been taken and all. And we don't know how much force we exactly applied also. So f dot s is not going to work, or integral f dot ds is not going to work. We have to use some other ideas. You may use this idea that work done by all forces is equal to change in kinetic energy. Work kinetic energy theorem, if you remember. Work done by all forces is equal to change in kinetic energy. Now the change in kinetic energy here is 0. Initially, the system was at rest. The hemisphere was at rest. Finally, also it's at rest. You're not given anything about it moving. In between, it moved okay, but finally it came to rest. So the total change in kinetic energy is 0. That means work done by all forces on the hemisphere is 0. Now, what all forces act on it? One is the force that we are applying, because we have to literally lift it and change its position. So work done by us plus. Now you can't stop gravity from acting. Gravity will anyway act. Okay, so work done by us plus work done by gravity should be 0. Do any of you think any other forces act on this object as its position is inverted? Initially, it's in contact with the ground. So that time normal force will be acting. But when you lift it and invert it, it loses contact. Normal force won't act. Even if it acts, the ground is a fixed surface. No, the point of contact with the ground won't be getting displaced. So normal force won't be doing any work even if it acts along the way. Like some of you may say, sir, what if we keep this point here itself and simply rotate it from this position to this position? In that case, normal force will be acting, but it won't be doing any work, because the point of action of normal force won't undergo any displacement. The rest of the body will move. So normal force will not do any work in this case. Let's consider it. We'll equate it to 0. Therefore, the work done by us should be the negative of work done by gravity. And gravity is a conservative force. Negative of work done by a conservative force is nothing but the change in potential energy. Okay, Aishwarya, good that you used this idea, but you said work done is negative of change in potential energy. If you want to use this, you'll get work done by gravity, not the work done by us. Generally, if you are asked a question like this, calculate the work required to do something on a system, it's the work which some person is doing, okay, or some external agent is doing. That is what you need to find out. So yeah, work done by us should be negative of work done by gravity. And because gravity is a conservative force, negative of work done by gravity is nothing but change in potential energy. Therefore, all the work that you need to do is give it the potential energy that is needed. Okay, and this is why I told you that idea that work is nothing but transfer of energy. Initially, the object is at rest. Finally, also it's at rest. So you are not giving it any kinetic energy. The only thing you have to give it is potential energy. So instead of discussing all this also, instead of using work energy theorem, you could have simply done this. Work done by us is equal to the potential energy given to the sphere, hemisphere. Okay. Now, how do you calculate change in potential energy? Final potential energy minus initial. Okay. Now, this is not a point object. It's an extended system whose radius is significant, 0.4 meters. Okay. So if you want to calculate its potential energy, you need to look for the position of its center of mass. That is why I asked you, where is the center of mass of a solid hemisphere? It's at 3r/8 from the base. So initially, or at the initial, in the initial state, its center of mass is here at a height 3r/8 from the ground. I'll take ground as reference. Finally, the center of mass is here at 3r/8 from above. 3r/8 from above will be 5r/8 from below. Why? Because total distance is the radius. So total has to be r. So from above, from the flat surface, if it is 3r by 8, then from the tip of the, not tip, what do you call? The topmost point, bottommost point of the curved surface, it should be 5r by 8. Okay. Why do we care about height of center of mass? Because potential energy of an extended system is mg into height of center of mass. Therefore, the change in potential energy now will be mg into final height of the center of mass from the reference level minus initial height of the center of mass from the reference level. That's all. Mass is given, I think, 2 kg. Gravity is 10. 5r by 8 minus 3r by 8 is 2r by 8. So 2 into 0.4 divided by 8. 10 is 0.4 becomes 4. All this gets cancelled. Answer is 2 joules. That's the energy that you need to give to this object just to invert it. Okay, very simple question, but it involves application of what we learned. It involves the use of the meaning of the quantities that we learned about till now. Okay, not directly formula based. Okay, so final potential energy is mg into final height of center of mass. Initial potential energy is mg into initial height of center of mass. And that is what we did here. Any doubts in this? Okay, now you all try to answer this directly. Like you don't actually need to write equations and solve. Suppose there is a rod lying on the ground. Rod or some object like this lying on the ground. Assume its mass is, okay, let's take m and its length is L. Okay, the horizontal length is L. Now what we want to do is we just want to make it vertical. That's all. Ignore the thickness of the object, okay, or the width of the object. Calculate the work required to do this. Very simple question. You don't have to use pen and paper also. You can ignore the width of the rod. Okay. Vanilla, your answer is correct only. Initially, the rod was at rest. Finally, also it is at rest. Aishwarya, any answer?
So 0.
Why? In the previous case, to invert that bowl, not bowl, that solid hemisphere, we had to do work. Here, why is it 0? Pawan, any answer?
No, sir.
Tell me the idea, Pawan. How did we solve the last problem? Okay. Vanilla, you only tell. You gave the correct answer. Again, you are unmuted, but I'm not able to hear your voice. Let it be. Leave it. See, we just need to change the orientation of the rod. So you can use that idea that work done by all forces is equal to change in kinetic energy. Change in kinetic energy is 0. So work done by us plus the work done by gravity should be 0. Means the work done by us should be negative of work done by gravity, which is nothing but change in potential energy. Okay. Instead of all this, you could have directly said the work we need to do is the potential energy given to the rod. That's all. And the rod is an extended system. It's not a point object. And for extended systems, to express gravitational potential energy, we consider the height of the center of mass. Center of mass of a rod is its midpoint. We know that. So finally, the center of mass is at a height L by 2. Initially, it is at a height 0. I told you not to consider the width of the rod. So initial height from the reference level is close to 0. That's all. Therefore, change in potential energy is final potential energy mgl by 2. Because mass is m, height of center of mass is L by 2. Okay, and initial potential energy is 0. So the work you need to do is mgl by 2. Aishwarya, did you understand?
Yes, sir.
Pawan, is it clear?